Welcome back to the Deep Dive. Today, we are getting into something absolutely critical, a real analysis of this code generation revolution that's happening all around us.
It really is. I mean, we're all feeling that incredible surge in productivity, right?
Absolutely. The speed is just, it's incredible.
Yeah.
But this deep dive is really driven by a simple and I think very necessary question. Can we actually trust the code that AI writes?
It's the question every single engineer needs to be asking. From, a junior developer on their first feature all the way up to a seasoned vet managing a critical pipeline.
And the scale is just mind-boggling.
The data is staggering. If you're writing code in 2025, you know these numbers. GitHub Copilot alone, just one tool, has contributed over 3 billion accepted lines of code.
3 billion.
And that's not all. Across the major tech companies, AI is now generating something like 30% of their new code bases.
That speed, it creates this almost irresistible pull. It feels like we've found the ultimate shortcut. We're moving faster than we ever thought we could.
We are.
But the mission of this deep dive is to get into the uncomfortable truth behind that. Yes, we are faster, but are we any safer? Or are we just, speeding up how fast we accumulate technical debt and security holes?
That is the core conflict right there.
Yeah.
Generative AI is this phenomenal tool for acceleration, but the output it's fundamentally statistical. It's just probability.
It's not thinking.
No, it produces code that, it often compiles, but it's unpredictable, it's frequently inaccurate, and it can be dangerously unreliable because it is missing one key thing. Context.
So all the institutional knowledge, all the why behind the code.
Gone. Our research is showing that while developers are completing tasks faster, they are spending an excessive amount of time later trying to fix vulnerabilities in that exact same AI-generated code.
Okay, so if the trade-off is write it fast with AI and then spend twice as long debugging the mistakes the AI baked in, that efficiency gain starts to look less like a superhighway and more like a detour through a minefield.
It's worse than just moving the work around. It's not just time shifting the debt. The reliance on this rapid generation, it creates a huge risk management problem. And we have a stat that really underscores this.
Okay.
A staggering 59% of developers admit to using AI-generated code that they do not fully understand.
Wow. I find that level of blind trust almost incomprehensible in an engineering world.
It's a huge leap of faith.
We would never, ever tolerate that from a human colleague.
Right.
It's especially not someone contributing to a mission-critical system. It just seems like the speed is so addictive that it's overriding that fundamental engineering principle of know thy code.
Precisely. We've outsourced the writing, but you can't outsource the accountability. And that leads us to our first really big question for you, the programmer listening. Would you merge AI code without reading it?
Right.
And if the answer is no, then why are so many developers relying on code they don't really grasp? The answer points to a deep cultural problem where the allure of velocity is just outweighing basic engineering rigor. We have to get that rigor back.
Okay, let's unpack this idea of the trust trap. Because I think the most dangerous thing about AI code is not that it fails in some big, obvious way.
No, it's much more subtle.
It's that it often works. The code looks clean, it looks elegant, it follows the syntax, it compiles without any warning.
It often passes the existing, the basic unit tests that were already there.
Exactly. And that functional correctness creates this massive false sense of confidence.
That false confidence is so pervasive because you, the developer, you're judging the AI based on its statistical output. The model generates code that is statistically correct.
Meaning it's just the most likely sequence of words, of tokens.
Exactly, based on the billions of lines of code it was trained on. But what it's critically lacking is that deep human context. It doesn't have the institutional knowledge of your company. It doesn't know about the undocumented business rules that were put in place 10 years ago.
Or the historical architectural decisions that, boxed you into a corner.
Or even just the simple team conventions that make code feel right for your specific project. It knows nothing about that.
It knows how to write boilerplate, sure.
Yeah.
But it has no idea why your team structured the internal payment gateway in that weird, specific way to handle some old vendor issue.
And that lack of context, it shows up in two really insidious failure modes that we're seeing developers struggle with right now.
Okay.
The first one is something we're calling logic drift.
Logic drift. That sounds almost philosophical, but you're saying it has real bottom-line financial consequences. So what's the practical definition?
Logic drift is when the generated code is, on the surface, beautiful. It's clean, it's readable, maybe even slightly optimized.
Okay.
But it fundamentally violates an invisible, unstated business rule. It's an error of domain knowledge, not a syntax error. The AI, in its mission to make code clearer, often just rips out the complex, messy conditional logic that was secretly serving as a domain constraint.
Okay, let's stick with that discount example you mentioned earlier, because I think it perfectly illustrates how you can actually lose money with this. So you have an old, messy function for applying customer discounts.
Exactly. You ask the AI, hey, refactor this ancient function. The original code was probably this ugly nested block of if statements, right? If is loyalty member, calculate loyalty discount. If has the other phone has promo code,
Where that little comment is doing a lot of heavy lifting.
a ton. That ugly structure, it visually enforced the critical unstated business rule. Loyalty discounts and promo codes cannot stack.
But the AI sees that messy structure and thinks, I can do better. I can clean this up, separate the concerns.
And it does. It creates two beautiful, clean functions. Apply loyalty discount and apply promo code. And then it calls them one after the other in the main processing flow.
And functionally, each piece works on its own.
Perfectly. But because the AI never had access to that one piece of institutional knowledge, the constraint that these two things are mutually exclusive, it creates this sleek new code that happily allows double discounts.
And this is the critical part. This isn't a runtime error. The app doesn't crash.
Nope.
The code deploys fine. It works fine for 99% of your customers. But for that one specific case, a loyalty member who also has a promo code, the system just quietly starts leaking revenue.
And you only find out 3 weeks later when the auditing team is reconciling the monthly accounts and something is very wrong. The code worked perfectly except for the one constraint that actually defined its business purpose.
Wow. That is the essence of logic drift.
It is. Now, the second failure mode is more about timing, dependency mismatches, and regression roulette.
Okay, and the danger here is that the AI is trained on a snapshot in time, right? And a 2-year-old snapshot is basically an eternity in software development.
It absolutely is. When an AI suggests a dependency or an import or even just a specific way of doing things, it's pulling from what was common and stable in its training data.
Which means it's often recommending popular but now deprecated libraries.
Or worse, far worse, libraries that have had critical security patches in the last 18 months.
So we use the AI to speed up adding a new feature, but in the process, we silently inject a known high-severity vulnerability.
That's the dependency risk in a nutshell. Take a specific example. Let's say you're integrating JWT authentication into a new microservice. The AI might quickly generate some code using an older pattern from the PydroTat library.
Okay.
That pattern, while it's syntactically valid, might expose your service to a widely known and already patched security flaw, like CVE 2022-29217. So by using the AI for speed, you've completely bypassed the current reality of dependency management and shipped a known liability.
And your security scanner is going to flag that immediately, forcing an emergency patch or just blocking the deployment completely.
Exactly. It's a huge point of friction.
So let's look at the other side of that coin, the regression roulette trap. This sounds just as subtle and hard to find.
It is. This happens when the AI optimizes code based only on the immediate context you give it. It has no visibility into all the downstream things that depend on that code.
Okay, give me an example.
Imagine you give it a slow SQL query to fix. The original query is simple. It uses an exclusion. Select from orders where status canceled. It's slow, so you ask the AI to optimize it.
And the AI, trying to be helpful, will probably suggest converting that to an inclusion, right? Which is often faster for the database.
Yep. It rewrites it to select from orders where status in pending, completed, shipped. Faster queries looks like a success.
On the surface, yes, but
But the AI didn't realize that the original canceled was also achieving a crucial side effect. Any rows in that table where the status column was NLL were also excluded by that operator.
and the new NN clause completely changes how NLL values are handled.
Completely. So if some critical monthly financial report relied on excluding those NLL statuses, your optimization just silently broke the report.
And because that financial report only runs on the first of the month, that bug just sits there, completely undetected in production for 3 weeks.
Until it surfaces and throws the whole audit process into chaos. And now the developer is tasked with reverse engineering and optimization they didn't write to find this silent data bug.
This whole category of failures, it really brings us to a more profound cultural risk, doesn't it? Developer skill erosion.
It does.
I mean, if the AI is writing 30% of the code and a big chunk of that code is subtly wrong, What does that do to the human developer's ability to even do their job?
It creates a dependency that is particularly dangerous for junior developers. If you're an experienced engineer, you have a solid foundation, you can look at the AI's output and immediately recognize a classic anti-pattern or veto a bad suggestion.
You're acting as the senior reviewer, the necessary filter.
Right. But the junior developer, they don't have that intuitive filter yet. For them, if the AI provides code that compiles and runs, it immediately has the weight of an infallible authority. It's like an oracle. They don't have the deep expertise in complexity analysis or system design to really critique the output effectively. So they end up adopting the AI's mistakes, its suboptimal suggestions, as standard practice. It actually erodes their ability to reason about the system from first principles.
It's the GPS problem, but for engineering.
Yeah.
If you only ever rely on the GPS for directions, you completely lose the ability to navigate when it inevitably fails or tries to send you down some road that doesn't exist.
That is the perfect analogy. We are replacing deep conceptual understanding with the passive acceptance of a statistical output. And this is why we have to underscore our second critical question. Who is responsible when AI code breaks production?
And the answer has to be unambiguous.
Completely. It must be internalized by every team using these tools. Accountability never, ever transfers to the machine. It is always the human developer who approved the merge, who signed off on the code review, and who deployed it.
Yeah.
The buck stops with the person typing the prompt.
Okay, so we have to move into what is probably the highest stakes territory here, security. This is where that lack of context and the statistical nature of the AI's training data, they're really combined to create active, harmful liability. And the research is clear on this, right? AI models trained on public code have learned all the bad habits.
The security risk is not theoretical at all. It's measured. One really prominent study we looked at found that when they generated over 1,600 test programs, a shocking 38.8% of those programs contained vulnerabilities that were exploitable by known attacks.
Almost 40%.
Yeah, and this is due to something called data pollution. The AI just learns from the weakest, most vulnerable examples in its massive training set.
Let's break down some of the specific security holes that AI seems to be particularly good at creating, starting with the all-time classic.
SQL injection. It's still one of the most common and dangerous flaws out there. Because the AI is often optimizing for what looks clear or simple, it defaults to these really outdated patterns.
Well, just concatenating strings together.
Exactly. It suggests concatenating unsanitized user input directly into SQL strings. This creates an immediate and frankly trivial point of entry for an attacker. We saw specific examples where Copilot, if you didn't explicitly tell it to use prepared statements, just defaulted to the vulnerable method.
So a junior developer asks the AI to build a simple search feature, and the AI inadvertently hands an attacker the keys to the entire database.
That's pretty much it. And the next risk is just as immediate. Hard-coded secrets.
Oh, yes.
AI systems will frequently generate authentication or configuration code that, for its own internal example, just embeds API keys or connection strings or passwords directly in the source file.
Things that should be in a secure vault or environment variables.
Right. But the AI puts them right into the source code, creating this massive instant data breach risk if that repository ever gets compromised or even just pushed to a public remote for a few seconds.
And then there's the really subtle one, the one that's domain-specific, flawed authentication logic. This is the one that automated tools often miss completely.
These are arguably the most complex and dangerous vulnerabilities in big enterprise systems. An AI can generate what looks like a flawless authentication flow.
Okay.
It seems to work perfectly in testing, all the inputs are sanitized, but because it lacks that domain expertise and critical human judgment, it might introduce a hidden logical flaw. Maybe a subtle way to bypass session management, or it fails to check two different authorization flags that are required by a specific business workflow.
And because these are flaws in the business logic itself, not just a known pattern like SQL injection, the standard automated security scanners, they just pass it as clean.
Correct. The vulnerability only shows itself during a full penetration test, or, much worse, after a real attack. And this forces the human developer to go on this huge forensic hunt, reverse engineering a big block of complex code they didn't even write just to find that one tiny logical hole. That's where all that extra time goes.
Here's where it gets really important. Let's shift from security to the hidden costs of performance and quality. The sheer velocity of AI generation, it seems to focus purely on does it work, often treating quality as sort of an optional extra.
And that quality decay just accelerates the accumulation of technical debt. When you use AI, you're not just getting a few lines of code, you're getting a new, complex thing that you now have to maintain for its entire life cycle.
So what are the classic telltale signs of poor AI quality?
First, just code bloat. AI solutions can be excessively verbose much longer than they need to be, or they use these overly complex structures where a simpler one would have been fine.
It's like you ask for a simple 10-line script and it gives you a 50 lines C++ implementation.
Yeah, exactly. It works, but now you have to maintain this iceberg when all you needed was a small cube of ice.
And we also see the constant introduction of anti-patterns.
Yes, the AI frequently uses a solution it learned from its dataset in completely the wrong context. It might use a complicated data structure it saw in an enterprise Java repository to solve a simple problem in a lean Python microservice. It's functional, but it's totally inappropriate for the architecture.
And that's compounded by inconsistent logic.
Right. The AI might solve the exact same caching problem in 3 different ways, across 3 different services in your app, which just complicates maintenance and adds a huge cognitive load for the human team.
And beyond just making it hard to maintain, the raw performance concerns are critical. The generated code might work fine on a developer's machine, but then it just falls over its scale.
Exactly. The AI will prioritize a quick, functional answer over actual algorithmic efficiency. So you end up with these brute force approaches or unnecessary loops instead of using known, optimized library functions. The code works fine until your user base doubles, and then you have a sudden, totally unpredictable outage.
And then we get to what is maybe the ultimate waste of time: hallucinations.
Hallucination is when the AI just confidently makes things up. It'll attempt to call APIs or functions that simply do not exist in the library you're using.
Wow.
One developer described the AI getting stuck in these loops of wrong info, citing documentation for a function that had been deprecated for 5 years. The human developer has to stop everything, debug this hallucinated function call, realize the AI is inventing things, and then start the whole process over. The time savings just evaporate at that point.
Okay, finally, we have to talk about the elephant in the room: accountability and legal liability. Even if the code works perfectly, the risk profile changes completely when an AI writes it.
The risk really falls into 2 very high-stakes categories here. The first is licensing and copyright. Because AI models are trained on these enormous volumes of open source code, they can inadvertently replicate copyrighted functions or code snippets that came from a repository with a very specific restrictive license, like a GPL license.
And the legal status of that is still a huge gray area.
It is, but the organization deploying the code holds all the liability. So a seemingly innocent block of code from the AI could open your company up to an intellectual property lawsuit just because the developer didn't recognize the unique pattern it copied.
That's a completely invisible risk.
It is. And the second category is compliance. Regulated industries, we're talking finance, healthcare, government systems, they require these super stringent audit trails and clear accountability for every single line of code that gets deployed.
And when an AI generates these complex blocks of code, it becomes really hard for a team to prove the reasoning, the review, and the verification process that went into it.
It makes it incredibly difficult to meet those regulatory obligations. The complexity that the AI introduces actually increases the compliance burden. It doesn't reduce it.
Okay, so we've laid out all the risks: the logic drift, security flaws, performance issues. The solution has to be a disciplined engineering playbook, right? We can't ban AI. We have to master it.
We have to. The core principle for every single developer has to shift from this blind trust to trust, but verify.
We have to fundamentally change how we see the AI. It's not a senior engineer. It's a really sophisticated junior developer. It's brilliant, it's fast, but it requires strict guidance and mandatory oversight.
And every single line of AI code has to face the same level of scrutiny, or ideally an even higher level than code written by a human colleague.
So to manage this new reality of velocity and risk, we need a multi-layered defense. Where do we start? What's layer 1?
We start with layer 1, proactive context and prompting.
Context management. This is crucial. If the AI doesn't know the rules of your project, it can't possibly follow them. So we need to move beyond just simple chat prompts.
We need to define the AI's foundation systematically. This is done by creating these architectural guardrail files, something like a .github copilot-instructions.md file or similar custom instruction files in your repository.
And these act as a persistent system prompt.
Exactly.
Yeah.
They automatically embed your necessary context into the AI's working session. You use these files to set your team's global standards.
So we can enforce our style guides directly, right from the start. We can tell the AI, Always use Pascal case for public classes, use snake case for function parameters, ensure every function has a doc string in the NumPy format, and always include robust error handling.
Precisely. By embedding those style and structure rules, you make the AI far more compliant from the outset. And crucially, you can also embed non-functional rules.
Like security constraints.
Yes. For example, when dealing with user input for database operations, you must always use parameterized queries via the DB connection. Create command method, never string concatenation. You proactively shut down that SQL injection vulnerability before it's even written.
Okay, so that's about defining the standards up front. What about refining the code once it's been generated?
This is where developers need to be trained in guided chat, using specific /commands. Instead of typing a vague request like fix this code, you use focused tools like explain to understand what a block does, fix to target a specific error, or test to generate some initial test cases.
The power seems to be in that targeted refinement, not just broad, blind generation.
It is. And a particularly powerful feature is the optimize selection command. If you have a 50-line loop that's running slow, you just highlight it and run that command.
And that forces the AI to focus only on that block.
Only on that block for performance or algorithmic efficiency. And it gives you the suggestions as inline diffs, which are so much easier and safer to review than getting a brand new 500-line file. It moves the whole process from generation to a reviewed refinement.
Okay, so we've guided the AI proactively. Now we move into what has to be the non-negotiable gate, layer 2. Automated scanning and analysis.
This is where we answer our third big question. Can AI-generated code pass a security audit without human intervention or specialized tools? And the answer, as we've seen, is almost certainly no.
So you have to integrate these tools directly into your CI pipeline.
Yes, and lock it down. Ideally as Git status checks that are mandatory for any pull request to even be considered for merging.
So what are the absolute must-have components for this automated layer?
First, static analysis. Tools like CodeQL, which is often built right into GitHub, have to be run on every single PR. CodeQL does these deep vulnerability scans, looking specifically for common AI-introduced flaws like injection attacks and security misconfigurations.
Okay.
Second, you absolutely must use linters and style enforcers, like TypeScript's ESLint or Pylint. These enforce type safety, consistency, and basic code health. If the AI introduces inconsistent logic or poorly typed variables, the linter fails the build. The PR is rejected.
And what about addressing that dependency mismatch problem, where the AI suggests old, vulnerable libraries?
For that, you need rigorous dependency management tools integrated into the process. Tools like OWASP Dependency Check or Dependabot or SNCC, they have to be employed to identify publicly known vulnerabilities in any dependency the AI suggests.
And it has to be a hard block.
A hard block. If a vulnerability is detected above a certain severity, the PR cannot be merged, period.
This leads to a really critical, actionable tip for every developer listening.
Always pin exact versions in lock files. Never, ever let AI-suggested dependencies use version ranges, like 1.0.0. If the AI suggests a library, you have to audit it, find the most current secure version, and pin that exact version number in your lock files. If you allow ranges, you're just risking silently pulling in a vulnerable version on the next build.
Okay, so we've guided it and we've scanned it. Now we hit layer 3. Enhanced testing strategies. The speed of AI means we can create code way faster than we can test it manually, so our whole approach to testing has to evolve.
This is where we catch the logic drift and the regression roulette. Standard unit tests running against mocked data are just not enough anymore. Validation has to go deeper.
What does that mean in practice?
It means your integration tests must run against production-like infrastructure. We're talking actual recent snapshots of your real services, your databases, and your configurations. If the AI's code depends on some subtle database behavior, like how NUL values are handled, only a real query against a real system is ever going to reveal that regression.
And we also need to move beyond simple output checks, too. You know, the basic unit test of, does input A give me output B?
Yes, we need to implement property testing. Property testing is fundamentally different. Instead of providing specific examples, you define invariance rules that must always be true no matter what the input is.
So for our discount example,
you wouldn't just test one loyalty member with one promo code. You would assert the property. For all valid order totals and for all discount combinations, the final price must always be greater than or equal to 0. And critically, the conditions loyalty flag is true and promo code applied is true must never both be possible at the same time.
So you're testing the underlying business logic itself,
Yeah.
and you're using tools that just throw hundreds of random valid inputs at it to try and break that rule.
Exactly. It creates this powerful safety net that's tailor-made to catch those subtle logic drift bugs that only show up in weird edge cases. And to prevent those silent regressions, we need regression guardrails.
How do we guard against that silent data corruption we talked about?
You implement snapshot testing for your critical data transformation layers. If you have a complex query or a function that processes thousands of rows of data, snapshot testing captures the expected serialized state of that result. It takes a snapshot.
Okay.
If the AI optimizes the query and the result changes by even a single byte, like catching an NLL value that shouldn't be there, the snapshot test fails, immediately flagging the regression before it ever gets near production.
And finally, just managing the sheer volume of testing this requires.
You have to run the full test suite on every single commit, not just the modules that changed. And since the full suite might take hours, this means you have to invest in test parallelization, sharding your tests across multiple machines to turn a multi-hour gate into a 15-minute verification. AI velocity demands test parallelization. It's not a luxury anymore.
And a final point on just the workflow itself. We need to manage the complexity of what we're asking the AI to do.
Absolutely. Adopt iterative development. Avoid asking the AI for these massive wholesale code refactors. Work in small, focused, agile pieces.
One function at a time.
One function at a time. Prompt the AI for a new utility, test it, review it, merge it, then move on. Trying to execute these huge changes all at once just makes it so easy to miss hallucinations and subtle logic bugs. Small pieces, quick validation.
We have spent a lot of necessary time on the risks, but all this caution is only useful if we also understand where AI provides real, reliable value.
It's an incredibly powerful tool for acceleration when you use it strategically. The goal is to eliminate the grunt work, which frees up human developers for high-level problem-solving and critical thinking.
So where are the sweet spots? Where can we generally trust AI code, assuming it still passes our whole validation playbook?
The first and most reliable use case is boilerplate and scaffolding. This is things like writing standard setters and getters, defining well-known REST endpoints that follow standard patterns, or generating configuration files, like for dependency injection.
So repetitive, low-risk, predictable tasks.
Exactly. They are ideal candidates for AI automation, and this feeds directly into rapid prototyping, or what some teams have started calling vibe coding.
Vibe coding. I like that.
Vibe coding is that fast, AI-driven development where you just quickly describe what you want, and you accept the AI's changes with minimal edits. It leads to these massive speed gains.
So it's perfect for MVPs, internal tools, hackathon projects.
Exactly. It lets engineers quickly explore concepts and test ideas without getting bogged down in all the implementation details.
But, and we have to say this again, that speed-first vibe coding mindset is incredibly fragile. It must never be applied to production-bound code without that complaint, human-in-the-loop review process.
Agreed. Vibe code is throwaway code until it has passed all 3 layers of the validation playbook. Another major sweet spot is just using the AI's vast knowledge for insight, especially in refactoring and optimization.
It can act as a sort of hyperfast knowledge base.
Precisely. If you have a slow piece of code, the AI can suggest more efficient, established alternatives. It can point you toward highly optimized standard library functions that you might not have known existed. One developer mentioned that they were completely unaware of C#'s built-in thread-safe blocking collection until the AI suggested it as an optimization for some concurrent processing they were doing. It saved them hours of searching through forums. It can be a phenomenal technical mentor.
Now let's flip the script a bit. If the AI is generating more code, that means the human review load is increasing dramatically. How can AI actually help with the review process itself?
We can implement AI as a code review assistant. Tools like Copilot PR Review can provide these automatic summaries of the changes, which makes the human reviewer's job faster. It highlights the intent and the scope of the change.
So it helps the human focus on the areas of greatest risk instead of just wading through lines of boilerplate.
Exactly. And moving beyond just summaries, you have tools like Graphite Agent, which act as a context-aware, active reviewer.
So it knows about your whole project.
Yes. These intelligent agents analyze the pull request, not just based on the changes, but with the full project context. The architecture, the style guide, the existing patterns. They'll flag logic bugs, identify missing null checks, point out inconsistencies.
So it enforces team standards before a human even has to look at it.
It's a critical guardrail. It catches those subtle flaws that human fatigue often misses, and the AI can even act as a security assistant, helping non-security experts detect and fix common threats by simulating attacks, like that SQL injection, and then immediately suggesting the correct parameterized fix.
But successfully integrating all of this, it requires a pretty fundamental culture shift in engineering teams, doesn't it? The way we work has to evolve to match this new reality.
The culture has to champion accountability and, most critically, transparency. Engineering managers should require developers to implement transparency by clearly labeling all AI-generated or AI-assisted code in their PRs. Maybe use a mandatory tag like AI-generated or Copilot-assisted.
And that's more than just a compliance checkbox. It's a vital psychological guardrail. When a human reviewer sees that tag, their mindset instantly shifts.
It does.
They stop looking for simple syntax errors, and they start looking for contextual errors.
Exactly. That tag forces the reviewer to ask those deeper questions. Did the AI really understand our domain model? Did it respect our specific architectural constraints? It primes them to look for logic drift. And beyond that, teams need to create a living institutional knowledge runbook.
A log of all the AI's failures.
Yes. This runbook logs every single mistake the AI made, why it happened, and how it was caught. Things like Copilot consistently generates vulnerable SQL for the inventory service, or ChatGPT suggests deprecated API methods breaking the payment gateway.
And this shared wisdom is then used to constantly refine that proactive prompting layer, layer 1.
You're turning past mistakes into future guardrails. And finally, we have to change the fundamental definition of when a feature is considered done.
The new definition of done has to expand.
It has to expand significantly. It can't just be it compiles and passes basic QA. It now has to include confirmation of AI generation compliance, mandatory property tests running against your core business rules, full integration tests against production-like infrastructure, dependency scans that enforce version pinning, and post-deploy monitoring for any immediate anomalies. If we connect this to the bigger picture, AI is a force multiplier. It multiplies whatever you feed it. If you pair its speed with weak guardrails, you're just going to multiply your outages. But if you pair that speed with strong automated testing and critical human oversight, you multiply your success. You free your human developers to innovate where it really matters.
This has been a deeply critical, but I think a very necessary deep dive into the code generation landscape. We've established that AI dramatically increases velocity, but its statistical nature, its fundamental lack of human context, its potential for logic drift, and its tendency to generate security flaws. It all demands rigorous, layered human oversight.
The bottom line is that 91% of developers still believe AI code cannot be used without human supervision. That's the reality, and that defines this new engineering rigor.
So AI is not some infallible oracle.
Not at all.
Yeah.
It is a powerful helper that excels at defined, low-risk tasks. But the human developer remains fully responsible and fully accountable for the code that ultimately ships to production. You are the senior engineer who signs off on the quality, safety, and correctness of all that output.
So what does this all mean for the future of engineering? It means we have to embrace AI not as a replacement for our rigor, but as a brilliant, fast, but ultimately junior member of the team. A team member that requires firm, well-defined, and highly automated guardrails throughout the entire delivery pipeline.
We spent a lot of time discussing the risks of developers relying on AI without understanding the code and the need to document the AI's flaws in runbooks. So the final provocative thought we want to leave you with is a cultural and technical challenge. How can teams evolve their knowledge bases, their internal design documents, their domain constraints, so that AI tools can truly understand those invisible business rules, like our non-stacking loyalty discounts, before they even write the first line of code?
That shifts the burden.
It shifts the burden entirely. From debugging AI errors to proactively managing and defining context for our AI assistants.
That is the future of intelligent systems design. Thank you for taking this deep dive with us. We have included links to the source research, the architectural guide templates we mentioned, and the specific automated scanning tools like CodeQL and OWASP Dependency Check, all in the description for this deep dive.
And if you found this analysis useful and actionable for your team, please click the heart or like button under the companion article. It really lets us know.
And if you want to keep up with more rigorous analysis of the AI revolution in software engineering, please subscribe on Spotify, Apple Podcasts, or YouTube.
And send us your feedback or any topic ideas via email. Until next time, stay vigilant and happy coding.